All right, everybody, welcome back to part two of our filtration physiology lecture. So now we're going to talk about a couple more concepts that seem to be tested. And with these concepts, they like you to know both conceptually what's going on, but there's also associated equations that you might be expected to memorize and essentially be able to plug and chug numbers that they give you into the equation to find an answer. So the first concept that we're going to talk about is called renal clearance. Renal clearance is the volume of plasma cleared of a substance in a defined amount of time. So basically what that is saying is how much stuff gets to the kidney overall, how much blood, plasma, fluid reaches the kidney. In a normal healthy kidney, the renal plasma flow is approximately 600 milliliters per minute. Remember, we said in the last lecture that of that 600 milliliters per minute, approximately 20% makes up the filtration fraction. So that means approximately 20% of the 600 is what makes up our GFR. And thus 20% of 600 is approximately 120 milliliters per minute. That means that 80% of it leaves the efferent arterial, or 480 milliliters per minute. The equation they'd like you guys to know for this is C equals U times V over P. So what does that mean? So C is the clearance of a substance. Remember when we say we clear a substance from the body, that we actually excrete it. It leaves in the urine. It goes into the kidneys, it gets filtered, and then it leaves overall. The blue highlighter is essentially talking about our term C, which is excreted from the body. U is the urine concentration of a substance, times V is the flow rate of urine. So it's how much stuff, the concentration, is getting there times how much, the flow rate, how fast it's getting there, divided by the plasma concentration of the substance. So in other words, this is saying our clearance is equal to how much stuff, how much solute is getting there, times the rate at which it's getting there, divided by what is left over in the plasma afterwards, because we're saying urine concentration divided by the plasma concentration. There are three key situations that they want you guys to kind of understand intuitively that we're going to draw out here. First, I'm going to draw in green, C equals GFR. Okay, so that says there is no net reabsorption or secretion. The molecule they like to use to test you here is something called inulin, and the reason for that is because it's not reabsorbed or secreted. So how much is filtered at the glomerulus and Bowman's capsule, again, I'll draw that with this green arrow right here, is how much is actually cleared from the body. So this is essentially going to go through the whole process of the nephron, and this is going to come down here and be cleared. Again, I'll draw our C for clearance down here. So the clearance is equal to the GFR. The amount of the substance filtered is all that is cleared from the body. There's no reabsorption or secretion of this substance. Next, I'm going to draw in orange, which is that C, or our clearance, is greater than our GFR. This tells us there is a net secretion. So PAH, or para-aminohippuric acid, is a good example of this. PAH is a good example because it is a molecule that is filtered at the kidneys, but it's also secreted. So in orange, we have our filtration at the glomerulus. And remember, back to our terminology, what does secretion mean? Secretion means a substance goes from the body into the tubule, into the nephron, to be excreted from the body. So secretion tells us that this process is occurring, that some level of substance out here is actually getting secreted into the tubule in here, and then eventually that is again being excreted. So now I'm going to draw a big plus arrow with the orange. You have GFR, highlighting in light blue, plus what is secreted, highlighted in light blue, equals what we said over here was our total amount of excreted, our C value, leaving the body. And the final one we're going to talk about is C is less than GFR. I'm going to draw that in blue. So this is telling us we have a net reabsorption, and glucose is the classic example they give here. So glucose is a substance that we can filter at the glomerulus, but we don't want to lose our glucose usually in a healthy kidney and a healthy individual, right? We want to retain our glucose. We need that glucose for energy. Additionally, amino acids are another thing that we retain 100% of, even if they get filtered at the glomerulus. We have lots of transporters to bring them back in the body quickly because we need the glucose for energy, and we need the amino acids for protein synthesis and overall well-being. So here we're saying that we have a certain amount of substance filtered, drawing the blue arrow. So there's filtration, so GFR occurring, but there's also reabsorption occurring. So this is why clearance is less than GFR. Remember, GFR essentially says that we're taking stuff from the tubules back into the body. So I'm drawing an arrow going from the tubules being reabsorbed into the body, and I'm drawing this near the PCT, or the proximal convoluted tubule, because this is where most of that process actually happens. So now we have, drawing a big plus sign, these two individual arrows. So we have GFR over here, highlighted in yellow, plus what is reabsorbed, and thus overall what we actually lose, what is cleared from the body, is less than what is filtered, because we filter some and then we take a bunch of it back. So in summary for this slide, I just want you guys to have an intuitive sense of what we mean when we say renal clearance. Be familiar with this equation right here. I'm highlighting in yellow. It's also in a red box for you guys. And really just be able to take numbers that they give you and put it into the equation and move it around and determine what is clearance, what is the flow rate value, things like that. And then have an idea of what types of molecules can be cleared at a greater rate than GFR or cleared less than GFR. And alternatively, what kind of molecules are cleared at the exact same rate as the GFR. Okay, next we're going to talk about something called renal plasma flow. So renal plasma flow, the definition is the volume of plasma flowing through the kidney in a defined amount of time. So again, volume of plasma going through the kidney in an amount of time. How do we measure this? So I said previously that approximately in a normal healthy kidney, you have about 600 milliliters per minute of renal plasma flow. We said there's about 600 milliliters per minute. About 20% of that is actually filtered, so 120 essentially, and then about 480 comes out the opposite side of the efferent arteriole. These are approximations based on normal kidney function. They can be looked up. However, how do we actually measure renal plasma flow? How do we actually estimate it? We use a molecule that we've talked about previously called PAH, or para-aminohippuric acid. Why then? Why can we use PAH as an estimate of renal plasma flow? The reason is because PAH is nearly 100% excreted from the body. So remember, what did we say that means? What does it mean to be excreted from the body? It means that the substance is actually leaving the body in the urine. So with my blue highlighter, again, I'm going to show you this is essentially going into the kidney and is ultimately leaving the body altogether. So if I draw my glomerulus and Bowman's capsule again, I'll use a green arrow for GFR, which is the filtration right here, and then I'll use a orange arrow for my secretion. Remember, we said secretion is when things go from in the body into the tubule to overall be excreted, which I'll use a blue arrow for excretion. So why is this a good molecule to estimate renal plasma flow? Because however much of this molecule reaches the kidney, however much of the fluid, the solute reaches it, leaves the body, and thus we can measure it. We can measure how much we give somebody and how much actually leaves, and that's an estimate, although slightly an underestimate, of their actual renal plasma flow. The equation they'd like you guys to know for this is estimated renal plasma flow equals U of PAH times V over P of PAH. Remember from the last slide we said that the U value is the urine concentration of a substance, PAH in this instance, V is the flow rate of the urine, and P of the PAH is the plasma concentration afterwards. So it's very similar to the equation used previously. It's called an effective renal plasma flow because it's not 100% accurate. It's an estimate that we're making of using the PAH molecule. The final thing we're going to talk about in this lecture is this idea of renal blood flow. So first we have to think about what is the difference between blood and hematocrit in plasma, because oftentimes the terms get used interchangeably, but they are distinct definitions. So blood is essentially the whole component of your intravascular space. So let's say this whole tube is 1.0. It's 1 unit of blood, so normal blood. Of this, approximately 45% or 0.45 is what's called hematocrit. So that's specifically our red blood cells. So blood composes our hematocrit plus our plasma, and the other 55% approximately is what is known as our plasma. So this includes our water, proteins, and various hormones. So the things they want you guys to know for renal blood flow is, again, definition and how to apply an equation to the concepts. So definition is it's the volume of blood flowing through the kidney in a defined amount of time. It's kind of a theme here with these definitions: volume of plasma, volume of blood, etc. It's approximately 20 to 25% of cardiac output. So really that is to say that the kidneys get a ton of our blood flow. And this is why our kidneys are very predisposed to ischemic changes. If they're not getting that blood flow, they're not getting that oxygen, they can go through ischemia pretty quickly. Two equations that I want you guys to know here. They're very similar, but it's important not to get confused with them. And again, if you guys know how to kind kind of insert the numbers that they give you, these are very easy equations to apply to, a clinical scenario, a clinical vignette in order to get questions right on test day. So let's look at the bottom one first. This is saying renal blood flow equals renal plasma flow divided by 1 minus the hematocrit. Remember, let's just use the kind of average renal plasma flow we talked about, which is about 600 milliliters per minute in a patient. So we're saying we want to calculate renal blood flow, which is equal to renal plasma flow, we're saying is about 600 milliliters per minute, divided by 1 minus a hematocrit, let's just use 0.45 to be simple. So if we plug these numbers in, we get a value of 1090 milliliters per minute equals to our renal blood flow. We can also check our math or check our work on that by essentially doing the opposite equation, right? So let's say they gave us 1090 milliliters per minute of renal blood flow and wanted us to calculate renal plasma flow. Well, now we would use the top equation. I'm going to do it in green here and say that renal plasma flow equals our renal blood flow times 1 minus hematocrit. And if our renal blood flow would have to be given to us because we need one to calculate the other, we're saying that renal plasma flow equals 1090 milliliters per minute times 1 minus 0.45 renal plasma flow equals. So then if we enter this into our calculator, which we're usually given in a test setting, we can figure out our renal plasma flow equals approximately the 600 milliliters per minute that we started with. So now we can kind of compare and contrast and confirm our calculations are correct. So with these equations, I really just think getting some repetition with them, doing some practice questions are the best way to kind of apply them. I think intuitively they could make sense to you, but even if they don't, really, you just have to kind of think about the physiology and kind of remember them for test day. These are equations that are not necessarily going to be given to you. You might be expected to memorize some of these. Fortunately, overall, there's not that many equations that you have to remember, but the ones we talked about in this lecture, I think you guys, it's worth committing to memory so that you can get these questions right on your test. Okay, that's it for this part. I'll see you guys in part 3 and we'll finish up filtration physiology.